Welcome everyone to Databases in the Microservices World. I'm really excited that we get to talk here at Pulsar Summit. This is going to be really, really fun. Here's the part where I tell you I'm definitely going to post the slides on my site tonight. You may come look on my site tonight, tomorrow, next week, next month. In about 3 months, you'll get tired of pushing a refresh and you'll email me. In about 6 months, I'll reply and say, no, I'm definitely going to post the slides on my site tonight. And I'll never post them at all. I've been that guy chasing the speaker and I never got the slides either, which is why I've posted the slides online already. You can go to robrich.org and you can click on presentations and you can grab the slides for this presentation. Let's head off to robrich.org. I'll click on presentations here at the top, and here's databases in the microservices world. You can get to the slides right now. Perfect. While you're here on robrich.org, click on About Me, and you'll get to this page that talks about some of the things that I've done recently. I'm a Microsoft MVP, a friend of Redgate. AZ GiveCamp is really fun. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp because it's always a lot of fun. Or if you'd like a GiveCamp in your area, hit me up on email or on Twitter, and let's get philanthropy installed in your neighborhood as well. Some of the other things that I've done, SQL Source Control Basics, mine is Chapter 8. That was a lot of fun. And I replied to a .NET Rocks podcast episode. They read my comment on the air. They sent me a mug. Woohoo! So that's a little bit about me. And I think we might have others that have joined us now. And so that's perfect. Let's dig into databases in the microservices world. Databases in the microservices world. We talked about this guy. Application architecture. Let's first start with apps. When we look at apps, we kind of have this history, and I love this visualization. We started out with spaghetti. We moved from there into ravioli, or into lasagna, and we moved from lasagna into ravioli. From a big ball of mud to end-tier architecture to now lots of microservices. And that's really cool. As we've gotten smaller and more condensed, each service does fewer and fewer things, and it's more about the integration between services that is so interesting. Looking at this more directly, on the left, we have a monolith, and on the right, we have microservices. Well, why did we use monoliths? We used monoliths because, well, deployment was hard, and we didn't want to do it very often. So we waited as long as humanly possible, and we deployed all the things in one place. That was great because, well, all of our private methods were all contained in the same single binary, and it was just the public interface that we exposed. Perfect. In time, we moved more towards microservices, and we did this because, well, we had containers and deployment was easy now. This is really, really cool. Each of those microservices does a small piece of the task, and each one can be upgraded or replaced independently. You'll notice in these microservices here on the right that each microservice could call other microservices, or a microservice might have its own data store. So if this microservice needs to get at the data in this microservice, it does a network call, and this microservice will reach into its data store and return that data. What's really cool about microservices is now we have these small pieces of functionality that we can upgrade and replace separately. A microservice. Each little piece does exactly one job. It's easy to deploy and scale that one piece with containers, and it's easy to replace them if we need to. One of the biggest principles of microservices is that each owns its own data. Now, this is important because now when we're not sharing data sources between microservices, we can upgrade that data store really easily. Who's using this column, this table? Well, if I'm not, then we know that that table or column is obsolete. Perfect. Well, kind of. As we move towards microservices, we often fall back into this. We have our application nicely distributed into lots of little pieces, but we have one big database. Well, why do we do this? Why do we have a monolithic database with microservices? Well, there's a couple of reasons. The most prominent is, well, the DBA said no. And I understand why the DBA would say no. You know, the DBA's goal is to keep the data secure. And well, if the data is in lots of little pieces, it might be difficult for the DBA to take control of that. But probably it has less to do with that and more about the scars that they have. You know, provisioning databases is hard. Provisioning new containers for applications is really easy. We just prop up the new ones, we move the traffic over, and then we kill off the old ones. We can't really do that with databases. We can't prop up a new database and then just kill off the old one because we would lose our customer data. So really what we need to get to microservices is a mechanism to ensure that authentication is in place and that the databases are backed up. And really, that's what the DBA is there to worry about. It's making sure that databases are authenticated correctly and that they're backed up continuously. So as we get to microservices that own their own databases, we may have a few bumps along the road. Well, if we have a monolithic database, we can treat it as if it was lots of little databases with a bounded context. Now, bounded context is kind of like this little circle around that portion of data that is responsible, that is part of this microservice. We can draw these little bounded contexts, these little islands of functionality, to start to treat our monolithic database as if it was small little databases. A bounded context is that portion that this microservice needs. As we look at a bounded context, we can look at an example like a shopping cart. A shopping cart needs the product catalog. It needs all of the product images, the product description. A shopping cart needs the ability to create orders. But it doesn't need anything more than that. It doesn't need to change orders. It doesn't need to own any customer details. It mostly needs to own the product catalog as a read-only experience and creating orders. By comparison, the fulfillment center needs a very different experience. It doesn't need all of the fancy images and product descriptions. At most, the only thing it needs from products is the product code. It needs the order, the line items, probably the shipping address, and it needs to be able to ensure that the credit card was processed. It also needs to update the order to show that it was fulfilled. So these bounded contexts are very different. The shopping cart needs the product catalog, and the fulfillment center needs to be able to change orders. We can see how those could be, in time, separate databases. As we get there, we could start to build microdatabases. Let's coin the term microdatabases to mean that portion of the data store that is owned by that microservice. Now, a microservice may have one or more microdatabases, but a microdatabase is never shared between microservices. Here's that mechanism that we like, where each microservice owns its own data store. Here's a microdatabase. Here's a different microservice and its microdatabase. We notice that when a microservice needs to call in to get data from another microservices database, it calls that microservice. It doesn't reach around. Now, that's interesting. Microdatabases, it's owned by one microservice, and other services call this microservice to get at or change the data. Well, so how do we do interesting things? Let's talk about joins. How would we do database joins in this arena? Well, a database join is trying to get at data that might exist in a different micro database. Well, how do we do joins? That's where Pulsar is really, really helpful in being able to have this distributed pub/sub system to be able to take data from one store and publish it into another store. If we publish our data into an enterprise service bus, then those things that need to consume it can grab it. And when it comes time to join, then we join on all the data that we've collected. We no longer need to reach out into that other data store. That's perfect. A micro database. So who owns the customer record? Is the customer record owned by the shopping cart? They need to be able to assign orders to that customer. Is it owned by the billing system? They need to store sensitive information like credit cards. Is it owned by human resources? Human resources is known to have lots of hidden data. Or is it owned by sales? They're probably the ones that see the customers first. Well, kind of. In sales, we have leads and prospects, and then those transition into customers. A lead may only have a name and a phone number. We don't have a full shipping address. But to make it a customer that can ship orders, we need to have a full shipping address. So do we have a table with mostly nullable columns? Well, let's separate this out into bounded contexts and micro databases. Let's create a new service that is a customer service. And this customer service owns the account number and the primary key that is that customer. And that's all. When sales needs to create a new account, they can call into the customer microservice to get a new account. When the shopping cart needs to go grab details about this customer, they can reach into the customer service to grab the account number. But then the shopping cart may have additional details about the orders that it's placed previously or this order that it's about to create. Billing can have its own customer profile details that talks about the billing materials associated with this customer, the credit card numbers. And human resources can have their customer profile with all the sensitive information. Each of these microservices can reach out for the account number from this customer microservice and then have their own data that is associated with that, the foreign key off to that customer. In this place, who owns the customer record? Well, that customer service, but the customer record is now only two fields, the primary key and the account number. Everything else lives in a profile associated with the correct microservice. So now we have micro databases. This is perfect. We got to that level of automation where we have backups and authentication automated. And we got to the point where we can now have micro databases, a database associated with each microservice. What's really cool now that we have lots of micro databases is that they all don't need to be the same type of database. They don't even need to be the same database vendor. I like this quote from me right now. So let's explore this. If they don't all need to be the same database type or same database vendor, well, now we can do some interesting experiments. We can pick the database vendor, the database style that best matches the microservices needs. Perfect. So let's take a tour through lots of database types. And in particular, let's see how Pulsar fits into this. Pulsar is a great data store, and we'll see when we need to use it. Let's look at different database types: SQL, NoSQL, graph, key value. There may be some here that might surprise you as we get closer into object and blob store, search, event sourcing, column store, and in particular, NewSQL. Let's dig into each type. So as we look at each database type, let's look at the characteristics, the pros and cons, the best use cases, and I'll give you some example databases. Now, I'm definitely not here to sell a database, but hopefully these search terms will get you to a database that is exactly the match that you need. So first up, relational databases. Relational databases we can think of kind of like an Excel spreadsheet. With an Excel spreadsheet, we have rows and columns. What makes a relational database different is every data in a column is the same type of data. So perhaps I'll have a zip code column and all of the zip codes will be the same. Or I'll have an address column and all of the data in that column will be addresses. I'll have a name column and all the details in the name column will be names. Now I have a really elegant SQL selection syntax, and it kind of feels English-like. That's cool. This database engine has been tuned to be really efficient at querying these SQL mechanisms. Now in time, I may need to do, well, relations between spreadsheets. Maybe I have a customer spreadsheet, customer table, and an order table. So a customer can have more than one order. So I don't just want to keep making more columns. So I'll create these relations between tables, a relational database. Now, relational databases, one of its primary characteristics is ACID compliance. Let's dig into ACID compliance. ACID compliance is atomic, consistent, isolated, and durable. Thus that acronym ACID, A-C-I-D. Atomic, it all succeeds or fails. Consistent, there are no partial transactions. Isolated, transactions don't overlap. And durable, once it's done, it's done. Everything in this transaction will either succeed or fail together. There won't be any partial transactions stuck in the database. As you grab these slides from roberts.org, you can click through to these blue links and see more information about these particular details. By comparison to ACID compliance, we have eventual consistency. Eventually, it will finish. A great example of eventual consistency is a credit card statement. I know at the end of the month when I get my credit card bill, all of those transactions are done. But if I swipe my credit card at the store right now, and then I go check my bill right now, that transaction may or may not be there, or it may or may not be correct yet. We'll write, and then we'll read right away, and we may not get the right answer yet. But eventually, we will get the right answer. So there's that squishy spot in the middle where it's like, well, it's not quite done yet. Another great example is getting coffee at Starbucks. When I go to Starbucks, I enter my order. It's not like they hand me the cup and then pour some water in it and then put some foam on top and then eventually put on the lid. Rather, they give me a handle, a note. They'll take my name. And once they finish building up the coffee, then they'll call me back and I'll get the entire thing there. Starbucks is eventually consistent. So eventual consistency versus ACID compliance. In relational databases, we have ACID compliance. We know that by the time this transaction comes back, by the time the query is complete, all of the data is updated and it either all succeeded or we got an exception and it all failed. Relational databases are ACID compliant. Relational databases. They're really great for having a strong schema, joins between tables. It is a very, very optimized and tuned engine, and we have this compatible familiar syntax. Probably, if you have a monolithic database, it is a SQL database. On the downside, it was optimized for storage size. So we can talk about third normal form or fourth normal form. That's a mechanism of avoiding data duplication so that we can store the data smaller. Now that's interesting, but that may not be ideal, especially in the days of terabytes and gigabytes of storage. Mostly, SQL databases were designed before multi-cores were a thing. And so for the most part, the way we scale a SQL database is we scale vertically. We get a bigger and bigger machine. Well, we may get to the point where a bigger machine is too expensive or not possible. And so it may be difficult to scale a SQL database. Because of that strong schema, I also need to migrate the schema. I need to tell it when that schema changes. Here's some examples SQL databases that you may choose. SQL databases are probably a good choice if that's your only choice. If you have a monolithic database, it's probably a SQL database. If you're just starting out and you're not quite sure what you need yet, a SQL database is a good place to start. Next up, let's look at a NoSQL database. Well, everything that's not SQL is NoSQL, so let's call this a document database. In a document database, we store JSON documents. Now, we could store other things, but the cool thing about a JSON document is we can nest properties, we can have different documents that have different properties. We also have a distributed mechanism where we generally have a cluster of machines that allows us to be more tolerant to hardware failures. Now, because we have a distributed system, we don't have ACID compliance, we have eventual consistency. So document database. Without a schema, we can evolve it a lot easier. We don't have to tell the database when our app changes. On the downside, our application probably does assume a schema for the database, so we have to do interesting things like querying into possibly null objects or being able to migrate data as it comes out of the database if it was an older schema. Now, these things are great for being able to sketch real quickly, but not having a schema may actually be to our detriment. There are no joins in a document database because each collection is pretty much an island unto itself. Now, it is distributed and denormalized, which makes it really well optimized for reads. That's cool. Here's some example of document databases. Document databases are great when we need to read all of the details. For example, a product catalog or a news site or a CMS, where we need to be able to pull out all the pieces of that page, the article, the title, the author's name, the author's picture, maybe the first few comments. All of the pieces come out in one spot and we can render that page quickly. Next up, graph databases. Graph databases are really, really interesting in that they focus on relationships. We have nodes and we have relationships between those nodes. And we're able to connect and store data both on the nodes and on the relationships. What makes graph databases special is this syntax that allows us to navigate. We could think of this as friends and friends of friends. Graph databases. So how is this different from a SQL table with two foreign keys? Maybe we just have a join table. Well, it's not all that different from a technical point of view, but its query syntax is what makes it so elegant. I can really, really easily do queries for friends and friends of friends, where in a SQL database, I would have lots of joins and it might get really messy. Graph databases. On the upside, we've optimized for that relationship experience. Friends and friends of friends. On the downside, we've traded other things for that. We can't really do cross-table joins very well in graph databases because it's really optimized for those relationships. Here's some examples of graph databases. Graph databases are great when you need to focus on relationships, perhaps a recommendation engine or a social network. These are great use cases for graph databases. Next up, key value databases. Key value databases are great in that it has a key and then it has a value that is a big binary blob or maybe a JSON text blob. We could think of this as a two-column table, one that has an ID and one that has kind of an opaque value, either text or binary. On the upside, the data doesn't need to be consistent between each of the values. Some values might be a JSON document. Some values might be simple configuration. It's really cool in that we can create mechanisms where we can store configuration data or state data, and it doesn't need to be consistent across them. These are great for get by ID type of scenarios where I can go grab that thing and use it straight away. Caching, for example. But it's not great if I need to do any queries by anything else. Basically, if I need to do a where clause on a field inside the data, I'm going to have to loop through every key in the database, deserializing this data using whatever format I use to put it there, and then go check inside that object to see if it matches. Key value databases are great for cache, configuration, user session data, places where I'm reading by ID. Here's some examples of some graph databases. or some key value databases. They're great for when I need to read by ID, but they're not great for when I need to where by anything else. Time series databases. Time series databases are great when I have a lot of time-bound data. For example, fast ingest of real-time events, when I want to query based on a time window. Now, what's really cool here is as I'm querying based on this time window, I may have multiple values. When we think of a spreadsheet and rows and columns, when I get to a cell in the spreadsheet, I have one value. In a time series database with a time window that is perhaps 5 minutes or a day, I may have multiple values. So now I can do really interesting things like, well, what is the max, min, average inside that window? A time series database is great at doing these kinds of calculations, creating these buckets, and then doing analysis inside the bucket of each value. On the upside, these windowing functions are great for these time-bound workloads. On the downside, we've traded all the other things. So it's not great for joins. It's not great for SQL speed. Time series databases are really good for, well, finding the high and low within a time bucket, stock ticker things, or IoT events, mobile device sensors, other types of event-bound data is really great for a time series database. Here's some examples of some time series databases. Text search databases. A text search database is really great for searching within a document to see where this keyword exists, or searching through a collection of documents to see which ones have this keyword. We may choose to pair this text search database with a natural language processing system and call that a search engine. But the natural language processing system and the text search are actually very, very different. Yet we often combine them together. A text search database has an inverted index. Imagine the index in the back of a book. Let's take all of the words in the book and let's index them. So we'll find all of the places where we have interesting words. Now we just go to the back of the book, we look for that word, and we can go to exactly what pages in the book have that word. Text search databases are great for searching text, for finding documents that have matches, for finding places in documents that have that keyword. Some text search databases actually add the schema at query time rather than at ingest time, which can be really powerful. On the downside, it's not really geared for anything besides this. You can't really store non-text data in a text search database, and stop words. In the English language, we have words that really don't mean anything. And, of. These are words that we may want to ignore in our database because, well, they really don't have meaning. But these words are very different when we go across cultures or across languages. The stop words in French or German or Spanish or Mandarin are very different than the stop words in English. So it's really easy for us to accidentally omit words that do have value by omitting stop words. So culture and language specific stop words are problematic. Text search databases. Here's some example of some text search databases, and we saw an example of this in the session that we just left. It's best used for finding keywords in a document or finding matching documents that contain these keywords. From there, we may do additional analysis. Now, the unfortunate part is text search databases are not great for doing other where clauses. So we may have a secondary index that keeps that additional metadata. Let me filter the documents that I'm going to search to the topics or tags or date range that I need. And then let's dig into each of those documents and see if it matches. Next up, object or blob stores. It's roughly like a file system. The key is the path. We could think of it like a file system, but it's kind of a synthetic file system. The value is a big binary blob. It's great for storing big things like videos, log files, backups. Now, again, we can't really where by anything else, much like a key value store. We can't find all of the database backups that happen to have this file. Rather, if we wanted to do a query like that, we would have to untar each backup and then look through it. That's a really expensive operation. We may choose to take our object store and add a relational store over the top of it so that we can use that relational system to keep additional metadata. Let's find the date ranges that match. Let's find maybe the file size or other characteristics about this so that we can filter down to just the blobs that we need. Here's some examples of object blob stores. Amazon S3 is kind of the de facto standard here. It's a great format that other databases use as well. Object stores are great when you need big blobs of stuff, but treating each blob may use a secondary mechanism. Next up, event sourcing. Apache Pulsar is a great example of an event sourcing database. With event sourcing, we will write things to the end of this queue, and then in a distributed disconnected mechanism, we will read from that. So here's two different clients, one that's on item 6 and one that's on item 8. And whenever they catch up, they do. The event sourcing database will keep track of all of the data. When it gets too old, we can see that 1 has already fallen off and 2 is getting stale. We can keep that queue of items and distribute it to all the systems that need to read it. An event sourcing system is asynchronous and disconnected. It's basically an enterprise publish-subscribe system. With event sourcing, we don't need to be connected at the same time. I don't need to call the other system and pass it the data. I can publish it to my event store, like Pulsar, and the other system can read it when they're ready. By comparison, we can also catch up with things. If this system was down, we can start reading wherever we need to and catch up. Or if the business rules change, we can start over reading from the beginning and get to where we need to. On the downside, well, what is the current version? I don't know. We need to play back through all of the results to get all the records to get their computed result in order. So ultimately, getting at the current version may be a little bit weird, and we may choose to have a separate data store that keeps track of the current version. Event sourcing. Here's some examples of which Apache Pulsar is a great example here. Other event stores allow us to do similar things. We can transmit data, and in a very disconnected way, we can read that data back out, filtering out those portions that we need. Event sourcing is great for compensating for hardware failure, since the two systems that are using this enterprise service bus don't need to be connected at the same time. Next up, column stores. Now, column stores are really interesting in that they kind of take that SQL relational experience and turn it on its head. On the left, we have a traditional relational database stored in rows. On the right, we have a column store. Imagine that we're storing countries. Well, there's only a certain amount of countries. And so we can compress this data really tightly because, well, all of the countries will, all of the data will filter out to just a few countries. A column store is great for compression. Column store is great for bulk reading and bulk writing. We get much better compression. We get fast seeks and bulk reads. On the downside, random reads and writes are slower. So if we can get to a certain spot and we can do analytics on that piece, a column store is a great way to do bulk analytics. Here's some examples of some column stores. Column stores are great for OLAP, analytical workloads, where we can do bulk reads and bulk writes. NewSQL databases. With a NewSQL database, we take the nature of SQL and we add distributed. In this case, we have a single store database with aggregators that accept queries and leaf nodes that store data in partitions. As you reach into an aggregator to launch a query, it will distribute that query to all the leaf nodes that have partition data that need to participate. Each partition will go grab the data, the leaf will then give it back to the aggregator, where the aggregator can create a deterministic result. With NewSQL databases, we still get ACID compliance, but we get distributed. We can think of this as SQL with an SLA, because to scale up our database, we just need to add more nodes. No longer are we bound to the amount of hardware getting bigger and bigger. We can add more hardware. NewSQL databases is much cheaper to scale than a traditional SQL database. On the downside, we may need to move data across the network to do things like joins. That's okay. We'll probably need to put all of our nodes on the same LAN, and we've already done that. So moving data between those LAN connected nodes is really not all that expensive, but it is slightly more expensive than doing it all on one machine. So a NewSQL database, here's some examples of that. A NewSQL database is great when you start outgrowing your SQL database, when you need to be able to get rid of that spinning wheel on your dashboard. That's when you reach for a NewSQL database that allows you to scale up beyond that one big machine. We've looked at lots of database types, and we can look at our micro databases and find the database type that best fits our specific needs. But we may also say, well, my chosen database has some of those and some of these too. A lot of database types are moving more towards hybrid databases, where it's SQL, but it has a JSON column to do NoSQL workloads as well. Or maybe it has time series and windowing functions. Hybrid databases allow us to have kind of a monolithic database, but also take on a few more workloads. Here's that money shot. Grab your camera and take a picture of this one. We'll look at all of the different database types, their description, and when they're best used for. As a recommendation, we can look at the different database types and choose the one that makes us happy. We looked at architectures. When we had microservices, but a monolithic database, we used bounded context to be able to separate that database into little data islands specific for each microservice. At the point where we got our database subscribed to automation enough to ensure that it's backed up and secure, authenticated, then we can move to micro databases, where each microservice truly owns its own database. These are the different types of databases. Because now we have different databases with micro databases, each one can be a different type. Recommendations. Generally in production, you want to use a database as a service. That will ensure that the vendor is responsible for point-in-time recovery and authentication and all of those things that allow you to sleep at night. If you want to use automation to ensure that your database is backed up and authenticated correctly, and by default, choose a SQL database. SQL engines are the most durable, the speediest, probably the most familiar as well. If you have a very specific need, reach for the database type that you need that exactly solves that problem. If you need to distribute data across many systems, use event sourcing, a package like Pulsar that allows you to connect different systems in an enterprise service bus. This has been a lot of fun getting to present at Pulsar Summit. If you're watching this online, grab me on Twitter at rob_rich, and you can grab the slides right now at robrich.org. For those who are watching live now, what are our questions?
Hi, thank you, Bob, for sharing your databases in Microsoft in Microservices world. It's a great talk, interesting and cool. We really love it. Since you have a recommendation for all those different databases, so I was wondering, is NewSQL database also distributed database?
Yes. What makes a NewSQL database different from a regular SQL database is NewSQL is distributed. It's across many machines, where a typical SQL database is only a single server. Now, you may have some SQL databases that do replication or log shipping or mechanisms to try and get to multiple databases, but those are usually bolt-ons, and each machine doesn't really act together as a single cluster. Rather, they act as separate spare machines. What makes NewSQL so novel is that you have many machines working in concert that allow you to scale horizontally, yet still maintain that ACID compliance. Great question.
Yeah, actually, I have an interesting question about that. Since we have so many different databases and people use it in different scenarios, how if sometimes when our company's business change and I might migrate from one database to another database, and there might be some problems in compatibility. So I was wondering, is there a simple way to manage different databases, and is there a feature that we can use different databases and migrate from one to another easily?
Good question. How do we migrate from one to another? Each database is really optimized to do specific things.
Yeah.
And so probably the best way to migrate between them is to publish the data into an enterprise service bus like Pulsar. And at that point, then the receiving system can process that data in the way that it needs to. Maybe it only subscribes to this topic, this channel, and only grabs the data that it needs to. If I'm moving from a SQL database to a NoSQL database, I might choose to just grab each row and serialize it as a JSON object. That isn't too bad. And now I can get from SQL to NoSQL. Going from NoSQL to SQL, though, is really challenging because now I have to normalize all of my objects and ensure that I have all of the columns represented. So migrating between database types is really difficult. I would advise instead, as you're crafting the microservices, choose the database store that really makes sense for that service and only migrate enough data to make that service run. All the rest of the data can stay in the monolithic database until you're able to move away from that monolith.
Yeah, so the decision to choose which database is very important for the microservices. Yeah. So do you have any recommendation for Apache Pulsar community and the project?
Yeah, definitely. You may grab your camera for this slide where that's the specific recommendations. Probably start with a SQL database because that's going to be the most consistent and the most universally used. And then if you have a specific need that exactly matches another database type, then you may choose to migrate into that other database type. Use an enterprise service bus then to connect the systems together. And that's where Pulsar really excels.
Yeah, okay. Thank you. Thank you very much for sharing the great talk. And thank
Definitely.
you.
This was so much fun getting to speak at Pulsar Summit. Thanks for having me.
Yeah. And thank you everybody for joining us today. And we have another session just after this, and you can just exit this session and enter the next one. Thank you. Thank you.
Sounds great.
Rob.
Thanks, everyone.
Bye.